Imagine a world where volcanoes erupt 100 times more powerfully than on Earth, constantly reshaping the landscape in a furious dance of fire and ice. That's Io, and our story begins here. Let's start by meeting Io. Io is one of the 4 large moons orbiting Jupiter, the so-called Galilean moons. It's roughly the size of our own moon, yet looks and behaves nothing like it. Here, what makes Io extraordinary? It is the most volcanically active body in the solar system, with hundreds of volcanoes actively erupting. Its surface is a riot of colors, yellows, reds, oranges, not because of vegetation, but because of sulfur and silicate materials vented from its depths. Volcanoes on Io aren't like your typical Earth volcanoes. They can shoot plumes hundreds of kilometers high, flood plains with lava, and constantly renew the surface. At this point, the big question looms. How can a moon, relatively small in size, sustain such intense volcanic activity for long? That question drives the rest of our journey. What if the most powerful volcanoes weren't driven by internal nuclear heat like on Earth, but by a cosmic tug-of-war? On Io, that's exactly what happens. Here's the mechanism behind Io's Inferno. Io orbits very close to Jupiter and is locked in a gravitational dance not only with Jupiter, but also with its sibling moons Europa and Ganymede. The result is an orbit that isn't perfectly circular but slightly elliptical. Because of the ellipticity, Io's distance from Jupiter changes slightly over each orbit. That variation means Io's interior is constantly being stretched and squeezed by tidal forces. Think of bending a paperclip over and over. Eventually, it heats up from friction. That's tidal heating. This internal friction converts orbital energy into heat. On Io, it's sufficient to keep large portions of the interior partially molten and to drive continual volcanoes. So the secret of Io's fiery heart isn't just its composition, it's its gravitational environment. That cosmic connection fuels the molten engine. From lava lakes the size of cities to plumes reaching hundreds of kilometers into space, the volcanic landscape of Io defies your expectations. Now we explore the visible evidence, what Io's volcanism looks like. One of the most dramatic features on Io is Loki Patera, a massive lava lake continuously churning. There are vast lava flows, such as from volcanoes like Amirani, which produce flow fields that dwarf terrestrial ones. Volcanic plumes on Io are huge. One eruption created a plume over 300 km high. The composition matters. The surface colors and deposits, sulfur dioxide silicates, tell us the interior is extremely hot and dynamic. Putting it together, Io isn't just active, it's hyperactive, and the volcanic features are on a scale and intensity that blow away what we see on Earth. Our view into Io's fiery world comes from daring spacecraft and cutting-edge research. Let's go behind the scenes of how we know what we know. Let's talk about how we discovered and studied Io. The volcanic nature of Io was first revealed by the Voyager 1 flyby in 1979, which caught dramatic plumes rising from the moon. Later, the Galileo mission provided detailed observations of Io's surface, hot spots, volcanoes, and orbital behavior. More recent studies, for example using the Juno data, estimate around 400 volcanoes on Io. Scientists continue to monitor Io from Earth-based telescopes and plan for future missions that will further unravel its mysteries. So our knowledge of Io isn't static, it's evolving, and there's still much to learn. Why should we care about a moon hundreds of millions of kilometers away? Because Io holds clues to how worlds evolve, and even what's possible elsewhere in the universe. Here, why Io is more than just a spectacular curiosity. Io challenges our understanding of geology. On Earth, volcanoes are driven by internal radioactive decay and mantle convection, but on Io, tidal heating dominates. That tells us geology can work differently. Understanding Io helps us interpret other worlds. Moons, exoplanets, bodies under tidal stress might harbor unexpected internal heat and volcanic activity. For example, large moons or planets close to their star may undergo similar heating. Io shows us the extremes to which planetary processes can go a world so active it wipes out impact craters, reshapes itself constantly. Finally, the mystery remains. Although we've made huge progress, we still don't fully understand how the volcanic plumbing of Io works, how heat is transported, how the magma reservoirs behave, and how this all ties into Io's long-term evolution.